Hello, everyone, and welcome to lecture 33 of computer architecture. Today is our final lecture, and we're going to be talking about address translation. So last time we started talking about virtual memory, and we said that with 32 bits, with 32-bit addressees, a process that is run, or a program that is running, which is called a process, is able to access 4 gigabytes of memory, which is 2 to the power 32. So we call this the size of the address space of the process. But there are a few issues here, which is that the system could have less memory, and also which we could have multiple programs running, and each one of those wants to have 4 gigabytes of memory. So we saw this is one example where a program has expects to have 4 gigabytes, but the system only has 1 gigabyte. So what do we do with this data, this memory that's out of range of the physical memory? And the other issue was if we have multiple programs, they're both expecting to put their data at the same address, but we can only give that address to one of them. So obviously we cannot just directly map this data to the actual memory in the system. So to deal with this, we made a distinction between the virtual address spaces of the processes that are running in the system and the physical address space of the system. And we said that the virtual address space is kind of a dedicated 4 gigabytes for each process, but this is only a logical address space. It doesn't physically exist. What physically exists is this physical address space, and we give these processes the illusion that each one of them has 4 gigabytes at its disposal by mapping these virtual virtual addresses to physical addresses in the actual memory. And we said to do that, we need address translation. And for address translation, we need to take a virtual address and translate it to a physical address. And we said that we do that at the granularity of pages. So every page in virtual memory translates to a page, it maps to a page in physical memory. And a typical size of pages is 4 kilobytes. So the virtual address can be divided into a page offset and a page number. And we said that the page offset doesn't need to be translated because the page offset differentiates bytes that are within a page. So it's going to be the same for both the virtual and the physical address. What we need to translate is the virtual page number, and we need to convert that into a physical page number. And one thing to note here is that the virtual and physical page numbers might be of different sizes, because the virtual and the physical addressees are of different sizes, because the amount of physical memory that we have does not necessarily need to match the amount of virtual memory that we have. And then finally, we said that if a page was not in memory, if I'm telling each process it has 4 gigabytes at its disposal, but I only have 1 gigabyte in my system, then obviously I'm not going to be able to put all my virtual pages in physical memory at the same time. So some pages will not be in memory. So if a process tries to access a page that is not in memory, what we do is we go and get that page from disk. And we call this a page fault. A page fault is when we don't find a page in memory and we go and we fetch it from disk. And page faults take a very long time because disk is very slow compared to our processor. So they're typically handled by the operating system. And we want to minimize page faults as much as possible because they're so expensive. So to minimize the page fault rate, we design memories to have large pages. That's why a typical page size is 4 kilobytes. We make them fully associative, so again, to minimize the conflict misses. So minimize page faults because of conflicts. And also we use smart replacement algorithms to make sure we make the right choice when we replace. And to do that, we run the replacement algorithms in software, and that's why the operating system interferes in this process. So this covers what we talked about last time. Any questions about last time's material before we talk about today, address translation today? All right, if there are no questions, then let's start talking about address translation. So what we said last time is, okay, so someone's asking me to explain again the smart algorithms. So I'm not going to explain what those algorithms are. You will take that later on in an operating systems course. But in general, because we care about minimizing page faults as much as possible, we really want to make sure that when we when we evict a page, we evict the best page that we can evict. So we evict the one that we're quite sure we're not going to use this in the future to avoid conflict misses. And to do that, doing this in hardware, running a smart algorithm in hardware is going to be quite expensive. And that is why we run it in software. Because if we want to put all this hardware to run these algorithms, they will take up a lot of area, and we don't want to do that. So we use smart algorithms, and we can afford to do that because the page fault penalty is so high, right? If a page fault is millions of cycles, then it's worth spending a few thousand cycles to run a smart algorithm to choose what your replacement is going to be, to avoid paying the millions of cycles due to a page fault. So this is the reasoning behind why we use smart replacement algorithms and software for pages. Okay. All right, so let's start talking about address translation. So for address translation, what we said is we want to take a virtual address and translate that into a physical address. And we said that in our example, we are assuming a 32-bit virtual addresses, so 4 gigabytes, and we're assuming that we have 1 gigabyte of physical memory, which corresponds to a 30-bit physical address. And the question was, how do we translate a 32-bit address into a virtual address into a 30-bit physical address? Now, we said before that the page offset remains the same because the page offset differentiates bytes within a page. So it's going to be the same for the virtual page and the physical page because it's indexing inside of the page. It's not selecting different pages. So what remains to be done is translating the virtual page number, which is 20 bits in this example, into a physical page number, which is 18 bits. So how do I take a 20-bit value and translate it to an arbitrary 18-bit value? Well, the answer is that we're going to use something called a page table. So we're going to use a lookup table. So what are page tables? A page table is something that we use in address translation. It is basically an array of page table entries. So it's an array of entries. This array is going to be indexed by the virtual page number. So we're going to take our 20-bit virtual page number. We're going to use it to index an array. And in that array, we're going to obtain a page table entry. And what is the page table entry going to contain? Well, it's going to contain the following. So the contents of the page table entry are as follows. It's going to have a valid bit. The valid bit tells us if our page is in memory or not, because our page could be in memory, it could be in disk, right? If the page is in memory, the valid bit will be set to 1. If the page is in disk, it will be set to 0. And if the page was present in memory, so if the valid bit was set, then the page table entry is also going to contain the physical page number. So this allows us to translate the virtual page number to a physical page number. And it's also going to contain other bits that we will use, and we'll discuss these bits later. Now, if the page is not present in memory, so if the page is not in memory, it's on disk, or maybe it's not even allocated, then in this case, we will have a page fault. And what the page table entry will contain is it will contain a reference to the page's location on disk. So there's a special space in disk called the swap space. This is where we put pages that are not in memory. And the reason we call it the swap space is because we use it to swap pages in between memory and disk. And what the page table entry will contain if the page is not in memory, so if the valid bit is 0, is it will contain some information to help us find this page on disk. Okay? Let me do an example to clarify this. So we said we want to translate a virtual page number into a physical page number. And to do that, we're going to have a page table, right? We're going to use a page table. The page table is going to be an array of page table entries. Each entry is going to have a valid bit, and it's going to have a physical page number. We're going to have other things that we'll talk about later. Okay? And what we're going to do is we're going to use the virtual page number as an index to index this page table. So this virtual page number is 20 bits. So we're going to use these 20 bits to index into this page table. And then in this page table, we're going to check if the bit is the valid bit is set. If the valid bit is set, then that means that the page is in memory. So we go and we look at the physical page number and we get our physical page number. And now we have our physical address that we can use to access memory. Okay. Now, if the valid bit is not set, what does that mean? That means we have a page fault. Okay, if a valid bit is not set, that means we have a page fault. Okay, so I will talk about what happens when we have a page fault. But before that, any questions so far? Is it clear to everyone how we translate a virtual page number to a physical page number using a page table? Okay, so now that this is clear, let's take a look at what happens on page faults. So if we have a page fault, we're going to perform the following actions. First, we're going to locate the page on disk, right? So the page, if the valid bit is 0, the page table entry is going to contain some information to help me know where the page is on disk. So we're going to locate the page on disk. We're going to go to disk. We're going to get this page, but we need a place to put it. So if there are free pages in the physical memory, great, we just put it there. If the physical memory is full, what do we need to do? We need to evict a page. And to evict a page, it means we need to have a smart algorithm, something to do. So we're going to have some algorithm that helps us decide what page to evict. And if the evicted page has been written to, what do we need to do? We need to take those updates and we need to write them back to disk, right? So if the evicted page is dirty, so we're going to have a way to track if a page is dirty, if a page has been written to. If the page has been written to, then we're going to write it back to disk first before we bring in the new page. Okay, so we find the page on disk, we evict a page. If the evicted page is dirty, we write it back, and then we're going to bring in the new page and put it in its place. So we're going to read the new page into memory. And then after reading the new page, we're going to update the page table. Why do we need to update the page table? Well, the page table tells us which virtual pages are mapped to which physical pages. But now what we just did is we took a physical page and we moved it to disk. And then we brought a page that was on disk and we moved it to memory. So we need to update the page table. Specifically, we need to update the page table entry of the page that we evicted to indicate that it's on disk, no longer in memory. And then we need to update the page table entry of the page that we brought in to indicate that this is no longer a disk, that it's now in memory, and we specify what the physical page number is. Okay. And then finally, after we're done doing all of this, we can resume execution from the instruction that caused the page fault. Okay, so this is obviously going to be a memory access instruction. So we now go back to this instruction and execute it. And now we know that the data is in memory, it's no longer on disk. Okay, so these are the things that we need to do when we handle page fault. And two important things to indicate here is that we need a way to evict a page, to decide what page to evict, and we need a way to mark a page as dirty. So to do that, we're going to have additional status bits that help us do that. First, to mark dirty pages, what are we going to have? We've seen this before. We've seen it before for caches. Right, we're going to have a dirty bit. So before with caches, to keep track of what cache lines were dirty, we had a dirty bit, and we're going to use the same thing. So disk writes take millions of cycles. So when we design memory, okay, it's not practical to design memory as write through. Okay, remember we only had dirty bits with write backs. With write through, we just wrote to the cache and also wrote to the next level in the cache. This is not practical with memory because disk writes are so expensive. So we don't want to have to write to disk every time we write to memory. So what we're going to do is we're going to design memory as write back, not write through. And because memory is write back, we're going to have to mark dirty pages. So we're going to have to set a dirty bit in our page table entry. So our page table entry, in addition to the valid bit and the physical page number, it's also going to have a dirty bit that we set if we write to the page. And when we come to evict the page, we're going to check if the dirty bit is set. If it is, we're going to write it back to this. Okay, clear? All right, what else do we need? Well, we said that we need to have some kind of replacement policy, and our replacement policy is going to need some information. It's going to need to keep track of some information regarding every page, and that information will be kept track of also in the page table entry. So the page table entry is going to contain information that's going to help the replacement policy make the right decision. Now, one possible replacement policy that is kind of a common one is using something, is to approximate the least recently used policy using something called a reference bit. Now, how do we do that? Because, keeping track of least recently used for, thousands of pages is really not practical. So we're going to have to approximate least recently used. And one way to do that is using something called a reference bit or a use bit. So a reference bit is a bit in the page table entry, and we set this bit to 1 if we access a page. So if I read or write to a page, I'm going to set this bit to 1. And what that means is that pages in memory any page in memory that's been accessed is going to have a reference bit of 1. Any page in memory that has not been accessed is going to have a reference bit of 0. Now, of course, any page in memory has been accessed at some point in the past. So what the operating system is going to do to make sure that the information is up to date is it's going to periodically clear all the reference bits. Okay? So the operating system periodically sets all my reference bits to 0, and then when I start accessing my pages, I'm going to set their reference bits to 1. Okay? And at some point, many pages are going to start to have 1, and then every now and then the operating system will set them all to 0. Now, what that means is that when I come to evict a page, if the page has a reference bit set to 1, that means it's been recently accessed. In other words, it's been accessed since the time that the operating system cleared all the reference bits. On the other hand, if the reference bit is 0, it means that the page has not recently been accessed. In other words, it has not been accessed since the time that the operating system cleared the reference bits. And based on that, we will evict the page if its reference bit is 0. So this is one possible way to approximate least recently used for a very large number of pages. And it uses a reference bit. And this reference bit will be contained inside of the page table entry. Okay, so if we go back to our drawing of the page table, here in addition to the valid bit and the physical page number, we're going to have a dirty bit, and we're also going to have a reference bit. Okay, clear so far? Any questions? Okay, great. All right, great. So now we have a way to do address translation from a virtual address to a physical address using a page table. And we also have a way to determine whether the page is in memory or on disk, to determine whether the page has been written to using a dirty bit so that I know if I evict it that I need to write it back, and also to kind of approximate a least recently used replacement policy. How large is this page table? So this page table is going to contain address translations for all the possible virtual page numbers to the corresponding physical page number, or to state that it's not valid, it's on disk. So how large is going to be the size of this page table? Well, let's see. Each entry is going to have a physical page number, so that's around 18 bits. And we're also going to have these 3 bits, the valid, dirty, and status bits. So that's around 21 bits. Okay. So a page table entry is not that large, but how many page table entries do we have? Right, 2 to the power 20. 2 to the power 20, right, times this many bits, right? That grows. Okay, that grows. So 2 to the power 20 is a very big number. That's millions. Okay, so this table is pretty large. Okay, so since this table is very large, can we put this table in hardware? Can we store this entire table on chip in the hardware? No, we can't. It's going to be way too expensive, right? It's going to be way too expensive. Okay, a typical cache, an L1 cache, is usually in the kilobytes order of magnitude. L2 cache might be a large number of kilobytes or maybe a few megabytes, right? So 2 to the power 20, just for a page table of one program, and you could have many different programs, this is way too large to store in the hardware. It's way too large to store on chip. Okay, so where can we store this page table? We're going to have to store the page table in memory. Okay, so let's take a look at this in more detail. So storing the page table. So page tables are very large. In our example, we have 20-bit virtual page numbers, which means that we need 2 to the power 20 different page table entries. That's going to be the size of my array. Each page table entry is going to have an 18-bit physical page number, one valid bit, one dirty bit, one reference bit. That's 21 bits per page table entry. However, there's one thing that's important to note here, which is that when I load data from memory, right, so when I want to load my page table entry from memory, I can't just load 21 bits, right? My hardware knows how to load at the byte granularity, and it has to be a power of 2 bytes. Okay, so I can either have 1 byte or load 1 byte or load 2 bytes or load 4 bytes, right? But I can't just load 21 bits like that. Okay, so my access to the page table has to be byte aligned, and it has to be a byte aligned to a power of 2. So I can't use 1 byte because that's just 8 bits. I can't use 2 bytes because that's 16 bits. So I have to use 4 bytes for my page table entry, because 4 bytes is 32 bits. So even though my page table entry in this example only needs 21 bits, I'm actually going to allocate 32 bits or 4 bytes for it. Okay? So we're going to use 4 bytes for every page table entry. So the total size of the page table is going to be 2 to the power 20 times 4 bytes. And that amounts to 4 megabytes. Okay, so every program is going to have a page table that's 4 megabytes large. And if I have many programs running in my processor at the same time, storing 4 megabytes on chip for every program or every process is way too expensive. Okay, so we cannot store all the page tables on chip. So where should we store them? Right, in memory. So the page tables are going to be stored in main memory. Okay, so every program is going to have 4 megabytes of main memory dedicated to its page tables. All right. Now, to be able to find this page table, because now a program needs to know where to find its page table. So to be able to find its page table, what the hardware is going to have is it's going to have a page table register that points to the beginning of the page table in physical memory. So if we go back to our diagram over here, this virtual address is going to be inside of some register, right? Because I'm going to use some register to read, or it's going to be coming from the ALU or wherever. So this virtual address is going to be coming from my processor, right? We're also going to have in the processor a page table register, and every program is going to have a different page table register, and this page table register is going to point to our page table in physical memory. And note that this is going to be a physical address, not a virtual address. Because if this was a virtual address, it means we'd need to translate it as well. Okay, and then we're just going to stuck in a loop, because to translate it, we need to find the page table, but the page table is a virtual address. So the page table register is going to be a physical address, and it's going to point to the location of the page table of the program in physical memory. Okay. Okay, so this is a good solution. Because the page table is too large to fit on chip, we're going to store it in memory, and we're going to have a register that tells us where to find this page table on memory. But now we have a problem. What's the problem? The problem is that now every memory access becomes two accesses, right? Now every time we want to access memory, now we have to perform two accesses instead of one. We need to perform one access for the page table to get the address translation, and then another access to. And by the way, typically, this page table representation that I showed you, this is a naive one. We usually use more compact representations of page tables. So, and in these compact representations, an access to the page table could be 2 loads or 3 loads instead of 1 load. Okay. So now every memory access is going to be an access to a page table, which could be 1 or more memory accesses, and then an access to the actual memory. Okay. So this is quite expensive. Imagine that every time we want to access memory, rather than doing 1 memory access, we're going to do 2 memory accesses. Okay, this is not very efficient, and also accessing memory is expensive. So even one, having to access a page table every time we want to do a load instruction is extremely expensive. Okay, so what can we do about this? If accessing our page table memory is very expensive, what can we do to avoid going to memory every time we need to access the page table? Right, exactly, caching. So the solution is that we're going to use a special cache for translations. So before we saw that we have a special cache for instructions and a special cache for data. And these allowed us to not have to go to memory every time we load an instruction, every time we load a piece of data. And we're going to do the same thing for address translations. Rather than going to memory every time we want to perform an address translation, we're going to use a special cache for address translation. So now our processor is going to have 3 different kinds of caches. 1 for instructions, 1 for data, and 1 for address translations. Okay? And we have a special name for this cache. That special name is the translation Lookaside buffer. So the translation Lookaside buffer is a special cache. Okay, it's a special cache for page table entries. It caches our address translations. And it does not need to be large, right? So the translation Lookaside buffer does not need to be large. Why doesn't it need to be large? Why is having a small TLB, the acronym for translation Lookaside buffer is TLB, why is having a small TLB enough? Why does the TLB not have to be large? There aren't many processes. Actually, there's quite a bit of processes running in your system. You'd be surprised how many different processes are running. Doesn't have to do with the number of processes. So remember, how large is a page? So we're going to have a page table entry for every page, right? But every page is 4 kibibytes. And what that means is if my program has good spatial locality, right, which programs usually do, then I'm going to need 1 address translation for every 4 kibibytes of instructions or 4 kibibytes of data that I access. Right, so I will go through, if I'm kind of executing my program, I have a sequence of instructions that I go through sequentially. I have to go through 4 kibibytes of instructions, right? That's 1024 instructions before, and all of that uses just 1 address translation. Same thing for data. I have to go through 4 kibibytes of data That's maybe an array of 1024 integers. All of that will go in one page. So all that 4 kilobytes of data is only going to need one address translation, because we're going to have one page table entry for every page. Okay, so for that reason, the page table does not need to be large, because every page or every 4 kilobytes of memory, every 4 kilobytes of instructions or data accessed only needs one page table entry. Okay, and so page table accesses have very good locality. Okay, they have very good locality, because even if I'm doing random access, if that random access like if I'm doing a binary search, for example, so the binary search accesses my array randomly, right? But if I'm doing a binary search in an array that's 1,000 elements large, right? All those 1,000 elements are 1,000 integers are going to be in the same page. So even if I have random access in my data or in my instructions, I would still have good locality when accessing my address translations. Okay, so page table accesses have good locality, so that the page does not need to be large. Okay, and since it does not need to be large, we can make it fast. Okay, another way, so we can have a small cache size, and this gives us low hit time. Okay, so the typical size of a TLB is 16 to 512 page table entries. That's the typical size of a TLB. Okay, and the typical hit time for a TLB is a half a cycle to 1 cycle. All right. Now, what about associativity? So since the TLB is not very large, doesn't have many entries, you have a small TLB size to ensure that I have low hit time. And at the same time, I can have high associativity to ensure that I have a low miss rate. Okay, so that I can design the TLB to have both low hit time and low miss rate by taking advantage of the fact that it does not need to be large. So I make this cache size small to have a low hit time, and I have a high associativity to have a low miss rate. And in fact, typical associativity for TLBs is fully associative. So TLBs are usually fully associative caches, okay, which is fine with this size, right? If I just have 16 to 512 page table entries, then a fully associative cache is perfectly fine for that, okay? And the typical miss rate on a TLB is 0.01% to 1%, okay? So you'll notice that TLBs usually have very low miss rate, very low hit time, okay? And all of that is because of the fact that we only need one page table entry to cover 4 kilobytes of instructions and data. So we change through our TLB entries much slower than we change through our instruction memory and data memory entries. Okay? Any questions about TLBs? Okay, let's illustrate what this looks like. So this looks like this, right? So here we have a virtual page number, and rather than using the virtual page number to index a page table, we're gonna have a TLB, which is a fully associative cache. We're going to compare our virtual page number to all the tags. Here the tag is the virtual page number. So we're gonna compare our virtual page number to all the tags. Okay, and we're gonna find if our page table entry is in the TLB, and if it's in the TLB, we're going to read the physical page number from the TLB and use that to complete our physical address. Okay. What if the page table entry is not in the TLB? So if our page table entry is not in the TLB, it means we have a TLB miss, and then we're going to go and read from the page table in memory. Okay. So to summarize, if the TLB valid bit is set to 1, that means we have a TLB hit. So we're going to read the translation from the TLB. If the TLB valid bit is set to 0, that means we have a TLB miss. And what that means is that the page table entry is not in the TLB. Okay? It doesn't mean that the page is not in memory. it means that the page table entry is not in the TLB. And in this case, we're going to go and we're going to try and read the address translation from the page table in memory. Okay. Now, when we go to the page table in memory, we can have two possible scenarios. The first scenario is that the valid bit in the page table entry is set to 1. And then that means that the page is in memory. So we load the address translation from the page table to the TLB. Or it could mean that the valid bit in the page table entry is set to 0. And that means that the page is not in memory. So we have a page fault. So we're going to go and fetch the page from disk. Okay. And one important thing to note here is that the valid bits in the TLB are not the same as the valid bits in the page table entry. The valid bits in the TLB are different. They have different meanings. The valid bit in the TLB tells me whether or not the translation is cached in the TLB. And that either causes me to have a TLB hit or a TLB miss. The valid bit in the page table entry tells me whether or not the page is in memory. And that will cause me to either hit the memory or have a page fault and have to go to disk. Okay, is this clear to everyone? Any questions about this? Okay, well, if there are no questions, then you could read more about what we covered today in section 5.7 of the textbook. And that is all for today, and that is also all for this course. I'm glad that we've been able to go through this course, and I hope that you guys enjoyed it. And as much as I would look forward to seeing you next time, unfortunately, this is all the time that we have in the semester. So I'm glad that you guys took the course. I hope you enjoyed it, and I hope to see you in the future in other courses. And best of luck on the final exam. Bye, everyone.